So what is the story? We are given a one parameter family of curves in the plane, and specifically we have one parameter family of lines in case of the Clairaut equation, and we found that the envelope, namely 2 root x, also satisfies the Clairaut's equation for the example that we considered, right. So what is an envelope? So given a one parameter family of curves, phi of x y a equal to 0. Your curve is given as a function, right, as a curve is given as an equation in x and y, but I am throwing in a parameter a. So we have a one parameter family of curves. An envelope is a curve that touches every member of the family, right. Consider for example the family of straight lines y equal to 2xc minus c squared. In fact, this is exactly the family of tangents to the parabola. This is the tangent to the parabola y equal to x squared at the point c comma c squared. So the exercise that I given earlier is already solved here, correct. This parabola is the envelope of the family of straight lines by very definition, because all these lines y equal to 2xc minus c squared, they are tangent. The line y equal to 2xc minus c squared is tangent to the parabola at c comma c squared, and I have a family of them, and this family and the parabola touches every member of this family. So the parabola is a envelope of the family of straight lines. You see some kind of a schematic diagram that I have drawn with a green colored parabola, and the tangents are drawn in red. So now how do I do this? I mean, so you take the equation y equal to 2xc minus c squared. So what is written there? Differentiate the equation with respect to c, the parameter. What do you get? 0 equal to 2x minus 2c. Now you have and then you eliminate c between the two equations. You got the original equation y equal to 2xc minus c squared, and you have the equation after differentiating with respect to c. You have two equations, eliminate c, you will get an equation in x and y, and that is the envelope, right. So now let me just put this down. In fact, if you do this, you get y equal to x squared. Now let me now write this as a formal rule. Here in the next slide it's coming. The next slide it's coming. Rule for finding the envelope of a family. You take phi of xy a equal to 0, eliminate a between the pair of equations phi of xy a equal to 0, and del phi by del a, you differentiate with respect to a, the parameter. You are getting another equation, correct. Now having gotten two equations, you can eliminate the parameter and get an equation between x and y, and that is your envelope. Is it clear? Is the rule clear to everybody? So now we will go back to the Clairaut's equation. The theorem says that for the Clairaut's equation y equal to x y prime plus f of y prime, this Clairaut's equation, we know that it has a family of straight lines as a solution. What is this family of straight lines? Y equal to mx plus f of m. Now if you take the envelope of this family, you will get a solution which also satisfies Clairaut's equation. Now this is a direct check. You have to take this y equal to mx plus f of m, differentiate with respect to m, correct, and eliminate m between the two equations. You will get that other relation. Remember, where did you get your y equal to mx plus f of m? From y double prime equal to 0. You differentiated the Clairaut's equation. You got y double prime equal to 0. The other equation was what? X plus f prime of y prime equal to 0. It is the second one that you will get when you carry out the rule for the finding the envelope. Take this equation y equal to mx plus f of m, differentiate with respect to m, what do you get? 0 equal to x plus f prime of m, and so that is exactly gives you the other equation, x plus f prime y prime equal to 0. Is that correct? So, this is an important example, and in the last line I written, in optics the caustics that you see is an example of an envelope of straight lines, envelope of light rays. In fact, Airy, the physicist, studied this phenomenon very carefully. He tried to find out that what is going to be the intensity of the light near a caustic. The intensity of light near a caustic is infinite as per geometrical optics, which cannot physically be tenable. So, geometrical optics is only an approximation, it cannot be exact, because if it were to be exact near a caustic, the intensity of light would have to be infinite as per Airy's discoveries. Okay. All right. I think we'll has everybody written down? Then we can proceed ahead, and I am going to give you a list of problems to work out, and here are exercises for you. Determine the general solution as well as the singular solutions for the following ODE: y equal to xy prime minus y prime upon square root of 1 plus y prime square. It is a Clairaut's equation. It is a Clairaut's equation, and so there will be a singular solution. And second exercise is an exercise on finding envelopes. Determine the envelope of the family of curves, circles touching the x and y axis. This is the very first exercise, the very first example we studied. Circles touching the x and y axis, and we obtained the differential equation for this family. And then the second part is circles of radius 1 centered at the points on the x axis. So, tell me geometrically what will be the envelope in case A? In the case of A, what will be the envelope? Circles touching the x and y axis, x minus r squared plus y minus r squared equal to r squared. What is the answer? What are the envelopes? You have to imagine these circles in the plane, all of them together, all the circles together. How do the circles look? No, in A, circles touching the x and y axis. The x axis is an envelope by definition. The y axis is also an envelope by definition. So, the envelope is simply xy equal to 0. But I would like you to get this from the rule for finding envelopes. For the second one, circles of radius 1, all the circles have radius 1 and centers on the x axis. What is the envelope? Y equal to plus or minus 1, that is absolutely correct. So, again this you can get analytically from the rule that I gave you. Any question? So, in each case find the ODE for the family and examine whether the envelope is a singular solution of the ODE. You have to examine whether the envelope satisfies the equation of the ODE. So, now we will take a pause for exercises. I have given you lots of exercises. So, let us take up these exercises one by one. Maybe you want to go in the reverse order. Maybe you can start with the last exercise, which is already on the screen, and you can work it out. The equation for circles touching the x and y axis is already given to you. X minus r squared plus y minus r squared equal to r squared. Differentiate with respect to the parameter, eliminate the parameter, and get the envelope. Let us begin over there. So, we will take a pause for tutorial. Now, let us come to the next bit in this thing, exact differential equations. Exact differential equations. So, first of all, what is an exact differential equation? The ODE m dx plus n dy equal to 0 defined on some region, right? The m and n are functions which are defined on some region in the plane is said to be exact if there is a smooth function f. Smooth means that it will have as many derivatives as the situation demands. Let us assume that it has two derivatives continuously differentiable, not a problem. So, let us assume that our understanding of smoothness means it should be twice continuous derivatives. All the three second partial derivatives exist and they are continuous. That is all that we really need. Such that m of xy is del f by del x and n of xy equal to del f by del y. This is the meaning of saying that the differential equation is a exact differential equation. That is, the components m and n are the x and y partials of a certain function f. I can state it in a different language, in the language of vector fields. In the language of vector fields, it just means that the vector field mi plus nj is a conservative vector field. That is exactly the same as the previous line. And the function f is the scalar potential. For the, when you have a conservative vector field, it has a scalar potential, and that is f. So, is the definition of an exact differential equation clear? Okay. So, suppose m dx plus n dy equal to 0 is an exact differential equation on omega with scalar potential f, then the general solution of the ODE is given by f of xy equal to c. Well, how do you prove this? Okay. So, let us check that f of xy equal to 0 satisfies the differential equation, correct. So, f of xy equal to c. How do you differentiate it? Use implicit differentiation, f sub x plus f sub y into dy by dx equal to 0. But what is f sub x? F sub x is m and f sub y is n, and that does the job more or less, correct. So, it is very easy. So, let us look at this example. This example will be familiar from the morning session. This differential equation is a homogeneous differential equation. We solved the homogeneous differential equation in the morning, correct. Let us take the same differential equation again. X squared minus y squared dx minus 2xy dy equal to 0. Let us check that this differential equation is exact. Well, it turns out that f of xy equal to x cube by 3 minus y squared x, that is a potential, that is a scalar potential. You just differentiate it with respect to x and you get x squared minus y squared, and differentiate it with respect to y and you get exactly minus 2xy. And so directly the solution is x cube minus 3y squared x equal to c. Yeah, is it clear? So, this example is an example. The example that we took in the morning happens to be a example of a exact differential equation, and the potential is x cube by 3 minus y squared x, and once you find the potential by inspection or otherwise, the solution is the potential equal to set equal to constant is the general solution of the ODE. Is this clear? Okay. Recall from your vector calculus courses that a conservative vector field is irrotational. Is that correct? First of all, what is a conservative vector field in physical terms? A vector field is conservative if the work done along a closed curve is 0. Item number 2, equivalently the vector field admits a scalar potential. So, condition A is integral along closed curve is 0, condition B is that function f, the vector field is the gradient of a scalar field. The third condition is curl of the vector field is 0. Now, the question is, are these three things equivalent? Let me repeat. A, integral over every closed curve should be 0. B, the vector field is gradient of a scalar potential. Item number C, the curl of the vector field is 0. Question is, are all these three things equivalent? Unfortunately, answer is no. A and B are always equivalent. A and B both imply C, but C does not imply A. The reason is very simple. Why C does not imply A? Of course, there are two reasons. I could just give you a straight away an example, that is one, and so okay, so C does not imply A and the matter is finished. But you would like to understand something, you would like to understand this, have a deeper understanding of this. Now look, when you say that the integral over every closed curve is 0, in some sense the condition is a global condition. To check whether the curl is 0 or not, what do you have to know? Suppose what is a curl? Curl involves the first partial derivatives of the vector field, correct? So at each, you take a point in the space, take a point in space, and at that particular point I want to understand whether the curl is 0 or not. So I just focus my attention on a neighborhood of that point and I have to check it. So if I tamper the vector field somewhere else, that condition is not going to change here. So the curl condition is essentially a local condition, whereas the other condition of vanish, the work done is 0 along every closed loop should vanish, that is a global condition. So a local condition generally will not imply a global condition, and that is the reason why C will not imply A. The third condition, irrotational, does not always imply conservative. Conservative implies irrotational, that is correct, but the converse is not true. So you see, so let us now, right, if you take the gradient of the vector field is a gradient of a phi, and if you take the curl of that, I am going to get curl of a gradient which will always be 0. Yeah, exactly. Right. So now let us, so this is something. Now of course we want to make this business quite independent of vector calculus. So let us look at it from first principles. Okay, so suppose that m equal to f of x and n equal to f sub y, then del m by del y will be what? The second partial derivative of f, first with respect to x and second with respect to y. What will be del n by del x? It will be f y x. Using the equality of mixed partial derivative, remember I am assuming that the function is smooth. I am going to get that del m by del y is del n by del x. This is exactly the condition that the curl of f is 0, curl of the vector field is 0. Remember our vector field is mi plus nj plus 0k, and m depends upon x and y, n depends only upon x and y. So when you write down the curl condition, you are going to get k times del m by del y minus del n by del x, that should be 0. The coefficient has been written down. So a necessary condition for the differential equation to be exact, or in other words, a necessary condition for the vector field mi plus nj to be conservative is that del m by del y equal to del n by del x. However, the converse is not true in general, and I explained to you intuitively why that is the case. Of course, that is only an intuitive explanation. I should be giving you a counter example. I should be giving you an example of an m and an n where del m by del y should be equal to del n by del x, but for which a scalar potential does not exist. Okay. Let us look at the following example. y dx upon x squared plus y squared minus x dy upon x squared plus y squared. This differential equation is satisfies the condition del m by del y equal to del n by del x, and that is an exercise. Check that this satisfies the condition del m by del y equal to del n by del x. Suppose if it is an exact differential equation, that means there exists a function f. Of course, the differential equation is not even defined at the origin. At the origin both x and y are 0. So, our domain is R2 minus the origin. So, that is where the, let me put that down on, so omega equal to R2 minus the origin, that is the domain on which we are going to be working. So, suppose that the differential equation is exact, then there must be a scalar potential f, that is m should be f sub x and n should be f sub y. Let us calculate the work done by the vector field along the unit circle. Unit circle is x squared plus y squared equal to 1. So, what is the work done? M dx plus n dy, the line integral. Let us take it along the counterclockwise direction, no problem. How do you calculate the line integral? You parameterize it, x equal to cos theta, y equal to sin theta. So, put y equal to sin theta. So, you see sin theta times d of cos theta, y dx minus x dy. So, sin theta into d of cos theta minus cos theta into d of sin theta. Denominator is sin square theta plus cos square theta, that is 1 in both the cases. So, but what is sin theta into d of cos theta? D of cos theta is minus sin theta d theta. D of sin theta is cos theta d theta. So, what are you going to get? Minus 1 d theta from 0 to 2 pi. And what is the answer? Minus 2 pi. The work done is minus 2 pi along this circle. Shall we proceed? Okay. So, let us now calculate on the other hand integral m dx plus n dy using the potential. Now, you are telling me that m is del f by del x and n is what? Del f by del y, correct? That is what you are telling me. So, the whole thing looks del f by del x and you are parameterizing the curve, right? Moment you parameterize the curve, dx is going to be dx by dt dt when you are computing the line integral, remember, and dy is going to be dy by dt dt, okay. So, it is going to be x is your cos t and y is your sin t, it is going to be del f by del x into dx by dt plus del f by del y into dy by dt whole thing dt. So, what is that? What is that thing? It will be ddt of f of ddt of f, the total derivative of f, correct. So, we are getting ddt of f of cos t sin t dt. Now, the fundamental theorem of calculus, it will be equal to f of cos 2 pi comma sin 2 pi minus f of cos 0 comma sin 0. F of 1 comma 0 minus f of 1 comma 0, which will be 0. So, we have calculated the work done by the vector field in two different ways, first directly and the other assuming that there is a scalar potential, and we are getting different results. It is a contradiction. So, this differential equation y dx minus x dy divided by x squared plus y squared equal to 0 is not exact, although it satisfies the condition del m by del y equal to del n by del x. So, the condition that the curl should be 0 does not imply that the vector field is conservative. Is it clear? So, the condition del m by del y equal to del n by del x is necessary but not sufficient for the differential equation m dx plus n dy equal to 0 to be exact. Please remember that many of the cheaper books do not dwell on this point and they simply say it is a necessary and sufficient condition, or they do not use the word necessary, the condition they will put conveniently. So, this is a very important point. In fact, you are going to study complex analysis next semester, as a continuation course. The entire complex analysis depends upon this one particular observation. This is the key point in complex analysis. Yeah, right, absolutely. Shall I proceed? The next slide. Okay. So, what is it? How should we salvage it? How do I get a necessary and sufficient condition? So, now let us discuss some geometry. A domain omega is said to be star shaped with respect to a point. I think before I go for star shaped, let us discuss convex domain. A domain omega is said to be convex. A domain omega is said to be convex if given 2 points A and B of omega, the line segment TA plus 1 minus TB, where 0 less than or equal to t less than or equal to 1 lies entirely in omega. So, for example, here you see under the at the bottom of the page a polygon, which is a convex polygon, correct. And so, there is an exercise for you. Show that the interior of an ellipse x squared by a squared plus y squared by b squared less than 1 is a convex domain. Show that a half plane is a convex domain and that a intersection of convex domains is a convex domain. So, everybody understands what is a convex domain. Take 2 points, draw the line segment, then the line, if the 2 points lie on the domain, the line segment must also lie on the domain. The notion of a convex domain is too strong, so we want to slightly generalize it. A domain is said to be star shaped with respect to a point P if given a point x, the line segment joining x and P lies wholly in omega. What is the difference between this and convex? Here one of the points is fixed, not moving, and the other point is an arbitrary point of the domain. So, look at this polygon, look at the star like polygon below. The point P is fixed. From P I can reach anywhere, but if I take x and y, then and draw the line segment, that will fall outside. So, this domain is a star shaped domain, but not a convex domain, correct. Is it clear? The difference between star shaped and, so the thing that is the theorem is, suppose omega is a star shaped domain, then the differential equation m dx plus n dy equal to 0 is exact if and only if del m by del y equal to del n by del x. In other words, the necessary condition becomes a sufficient condition provided the domain satisfied certain geometrical conditions. Some domain geometry is required for you to pass from the local information to the global information. The necessary condition in this case becomes a sufficient condition provided the domain satisfies certain geometrical hypothesis such as star shaped domain. In particular, every convex domain is star shaped. So, convex is okay, but convex is too strong. Star shaped is fairly nice. There is an exercise which shows that the plane minus the negative real axis is star shaped but not convex. the plane minus a point is not star. So, star shaped is a very nice condition, easily describable condition. Somebody mentioned simply connected. That is a further generalization, but it is more difficult for me to explain to you what a simply connected region is. It does not have a simple description like this. Okay. So, we will stop here today and we will continue tomorrow.